Hello and welcome back to Juno, New Origins, formerly known as Simple Rockets 2. Thank you very much for joining me in today's video. Last time out, we started the career mode and created this, the car. A nice, simple name for it isn't really a car, it's a little RC, I don't know, an RC little thing with winglets on it, with fins on it, whatever you want to call it. It's a tiny little thing. I say tiny, it's a bit bigger than your home cars that you're going to get, but it is fairly small. So we made this, and as I said in that video, quick and easy money. Did not take a long time to build, and as you can see in the middle of your screen at the top right, top right middle, that's a coordinate system right there. Current money, 186,000. That is a lot of money made off this, which I made in the last video. I've just taken this out again and again and again, doing missions with two changes. I increased the torque ever so slightly, and I enabled rear wheel steering. That is all I did, and it has made me this much money. Great, that is a really, really good start. Speaking of good starts, I'd like to thank everybody for actually watching the first two videos, all of the people who have been watching it, liking, subscribing to the channel. I really do appreciate it, and if you could continue to do so, continue to like the video and watch the video all the way through, it would really help with the YouTube algorithm. I'm not very comfortable with the fact that I've got to say this, because I normally say this at the end of the video, but apparently this is the way things go. So please do bear with me on that. In this video, what I'm going to do, as you may have gathered from the thumbnail, from the title, is I'm going to take the rocket approach. So if I just go over to the tech tree, I'm going to start with this approach here. Now, I have 110 tech points, but I have intentionally not used them. And that is for people who may have started with the backyard scientist approach. What do you want to do with that particular approach? And how are you going to approach it? Because you are not going to have the tech points for it. So my goal here is to, within 6k, so the 5k you get to start with plus that 1k signing bonus, within 6k I want to be able to achieve this first mission, and then we shall see what we'll do beyond that. However, I also want to do this applying some actual rocket science. So I'm going to try applying actual equations to the rocket that I build and work it out in a scientific way, in a way that I would if I were doing this and building an actual rocket. And I want to see if my calculations A, are correct, 2, if my assumptions will end up being correct, and 3, if I can actually do it. So if you want to see a rocket scientist attempt rocket science in a game about rockets, make sure you stay tuned. Okay, here we are with a new craft ready to go. It's a disk. It's a command disk, nothing else. So we're going to add a few bits to this. Let's go ahead and add a nose cone, because we are going to need that. A fuel tank, because we are going to need that. And a little rocket, or rocket engine. There we go. Job done. Ready to go. That's it. Let's go ahead and launch, and this should make it. No, it's not going to make it. So, looking at this, I want to take in a bit of information and figure out whether, first off, I want to double check some of these things, and then I want to add a little bit more to it so that my guess is a little bit more, or my assumptions and my educated guess as to how far we are going to go is a little bit more accurate. So how far are we going to go? Well, that depends on the delta V. The higher the delta V, the further you go. The reason being, for those people who may not be used to either doing this in this title or Kerbal or anything else, or just do it intuitively and do not really look at this data, which is perfectly fine, or just are interested in rocket science and how we actually do this. We'll start with the delta V. So the delta V, delta means change of. We can have deltas of anything, delta T, delta S. Delta T is change in time, delta S, change in displacement, delta X, change in distance, delta V is change in velocity, delta P, change in pressure, delta rho, change in density, so on and so forth. Delta H, change in height. So we can have lots of deltas. In this case, we have delta V, change in velocity. What this tells us is that this rocket that we have has the ability to change velocity 1, 2, or at a rate, a total amount of 1.4 kilometers per second. Now, what that does not mean is that this rocket is going to get to 1.4 kilometers per second just like that. There are other things that need to be taken into account. For example, if you go straight up, then yes, you should get the 1.41 kilometers per second. If you go straight sideways, you should also get that 1.41 kilometers per second. But if you go up and then go sideways, that is going to change things, because then you've introduced trigonometry and you're going to have a sine of something. Your thrust is going to be slightly different. You've got to have a component of thrust in the y direction, or a z direction I suppose you're going to say, and a component of thrust in the x direction. You may even need a component of thrust in the y direction. Three-dimensional space. All of this will be taken into account. Also, if you are in space and you need a delta, and we have this delta V for example, if you spend 500 of it, so let's say you burn a rocket for a short period of time, you will spend 500 of it. What that means is that your delta V now is 901 meters per second. Now, if you continued spending that in the exact same direction that you were going, and let's say you start at 0, for example, you were stopped in space, then you're going to reach your 1.41 kilometers per second. But if you decided to flip your rocket around and then burn in the other direction, the remainder of what you had, because it's velocity, it has a direction as well as a magnitude. So the magnitude is the speed, and the direction is where it's going. That's the vector. So it's saying which direction are you looking in. So if you were to burn then in the opposite direction, so you've done 500 in one direction, 901 in the other direction, exactly opposite, your net is going to be 401 in the opposite direction to where you originally burned. And that's all your delta V spent. So it does not necessarily mean that this is your max speed. All it means is that this is the amount of change you can have in your speed from whatever speed you are at. If you are doing 500 meters per second in a direction and you burn in that direction, you can increase speed to whatever it is. If you burn in the opposite direction, you will decelerate, but you are still using delta V. Okay, that's probably a simple explanation as to what delta V is. How do we calculate the delta V? Well, the delta V is calculated. There are a few or a couple of different ways to calculate delta V, but once it was derived by a British person in the 1800s, I believe, then there was a Russian person in the 1900s, which is who the equation is named after. I cannot pronounce his name, and then I think there was a German fellow who did it a few years later, and then was it an American as well that did it a few years later? Everybody derived it individually and independently, and the most common form of the equation is by the Russian fellow. So this equation is delta V, or you could use delta U if you want, is equal to the equivalent exhaust velocity, which I can go into a little bit later, multiplied by the natural log of the mass that you start with on the craft, divided by the mass that you end with, i.e. the mass less the propellant that is used. Sounds a little complicated, but it really isn't. Let me explain how we calculate all of this. Equivalent exhaust velocity, I'm just going to throw that out for a moment, and I'm going to replace it with two other terms, because these two terms multiply together to give you the equivalent exhaust velocity. The first term is this one right here, ISP, which currently says not available. I'll put that to stage 1. There we go. That is the specific impulse. All the specific impulse is the amount of thrust that you have multiplied by the time you can burn that thrust divided by the weight of the craft. That is your specific impulse. Nothing more than that. So this one's specific impulse is 155. There are a couple of other ways of calculating specific impulse if you wanted to, but that is one way of calculating it. The other thing that we are going to multiply with the specific impulse is gravity. So gravity on this planet at the altitude we currently are is being read to be 9.76. So 9.76 meters per second, slightly less than that of Earth. So let's go ahead and multiply those two numbers together. 155 multiplied by 9.76 gives us 1512.8. So that is actually our equivalent exhaust velocity. You'll notice that we have exhaust velocity here, and the equivalent exhaust velocity is less than that, because I have said it is 1512 meters per second. Our exhaust velocity here is 1540 meters per second. I will talk about that maybe a little later if people are interested. I may talk about that. Anyway, so what we then need to do is we then need to multiply that number by the natural log, and I'm not going to go into natural logs, it's just log to the base of E. E is Euler's number, which is just one of the special numbers, just like pi, just like the golden ratio, just like phi. Euler's number is another special number. 2.18281828 does not continue as 1828, it is actually an irrational number, goes off to all sorts of numbers, but just like pi, it is one of those numbers that crop up and are used heavily in a lot of different things, including electronics, for example. We use Euler's number quite a bit. So, natural log of two values. The first value is 141. So that is the mass of this rocket with all of its fuel on board, all of its propellant. Then what we need to do is we need to find out what the mass of the fuel is, 85.5. So, and actually it just tells us that there. So what we then need to do is take away that 85.5 from 141. So you should end up with, there you go, 55.8. Wait, what? Is that? Yeah, okay, whatever. I think there's slight rounding there. I think there is a little bit of rounding going on. Anyway, so we'll have 55.8. And that gives us a delta V of 1402 meters per second, which is less than what we have here. The value that I've calculated is a more accurate delta V than what we have supplied over here. So I'm going to use this value of delta V, and this is the reason I wanted to calculate it. I wanted to essentially confirm and double check. Now, that's one thing that we need to take into account. The other thing that we need to take into account is that we are in a gravity field. Now, I know I said delta V is there's a multiplication by gravity, but that is looking at the thrust of our vessel fighting gravity. What we haven't done is, or the thrust of this, the engines and how they work with gravity. What we haven't done is taken a look at gravity itself pulling us down. So what we have to do is we have to actually take away The burn time multiplied by gravity, if I remember correctly. Now, I could be wrong. It has been years and years since I studied this, but I believe the next thing that needs to be done here, because I'm fairly sure we are not going to get to this delta V. So the next thing that needs to be done is we need to take away our gravity, which is 9.76, multiplied by our burn time of 44 seconds. That gives us a new delta V of 973. So this vessel should be able to reach 973 meters per second. However, there is one other thing that is missing: drag. Now, drag generally is not a massive deal, because as you start plummeting or start rising through the atmosphere, the atmospheric density drops, drag starts falling away, because one of the key calculations, or the calculation of drag, relies on a few things. Number one, it relies on the velocity of the craft, velocity squared specifically, so your drag will increase at the rate of the square of velocity, which means that the faster you go, drag does not increase in a straight line. It increases with a curve, and that curve gets steeper and steeper and steeper, or the line or the gradient of the curve gets steeper and steeper and steeper. And that is why it is so difficult to get cars, for example, going incredibly fast. You'd think, well, cars have been able to get to 60 miles per hour for years. We've got cars now just about getting to 300 miles per hour, but getting beyond that, it's going to get even harder, because aerodynamically you're going to have to start doing a lot of things with the car. In fact, you look at all the fast cars, they are very, very aerodynamic. Whereas if you look at the slower cars, there's loads of different shapes to them, and all of them manage to reach 60 miles per hour, all of them manage to reach 90, 100 miles per hour. Not a problem. But it is, the faster you go, the harder it gets, and the more thought you have to take into developing the aerodynamics. And the reason for that is that aerodynamics require, or take the calculation for aerodynamics that we use, or the figure, is called the coefficient of drag. And that is what the aerodynamics designs are trying to do. You're trying to reduce the coefficient of drag, trying to make it slippery, as it were, aerodynamically slippery, so that the air just flows right over it, doesn't sort of pummel into it. So if you had like a slab, the air would just be hitting it over and over and over. That is not aerodynamically efficient. That is a very high coefficient of drag. If you have a needle with a very sharp point, and the metal around the needle is very smooth, no bumps, that would be a much better coefficient of drag. In fact, that would be an excellent coefficient of drag. Very, very low, which means the drag will be very, very low. The equation is drag is equal to half rho, which is the atmospheric density, which is why I mentioned that, rho, v squared, s, which is the area that the air is going to be hitting, so the cross-sectional area, and then the coefficient of drag. So those things all get multiplied together, and that gives you your drag in newtons. We need to take that into account. However, before we do that, we need to do a few other things. I think, and the problem with the drag one is going to be, we're going to be accelerating. We're going to just have to guess the drag. So the first thing I want to do, if we're down to 900 meters per second on the delta V, I would think that even though we've got that thrust, we are not going to be able to get to the 25. So at this point in time, I'm just going to start using a bit of intuition now. So that's down to 918, but I'm not fussed about that just yet. At the moment, I'm working on acceleration. Now the acceleration is very easy. At any given point, take the velocity, and then, or take the mass of it, and then take the force of it. So you can just use F equals ma for any given point. We cannot calculate the acceleration, say, oh, well, what's the acceleration going to be after 6 seconds? What we then have to do is work out how much fuel is burnt after 6 seconds, what thrust is it giving after 6 seconds, and all of that kind of stuff. How much is the gravity weighing it down? And then you can work out the acceleration at any given point. But if we just want to do it just at an instant, say this is where we are, it's just a simple F equals ma. But we cannot sort of graph it up and say, well, the acceleration is going to be constant, as I mentioned before. I'm going to top up the fuel here. Let's bring this up to, let's do 1.8 meters, shall we? Remember, we have 6,000 to spend. Oh, what on earth have I just done? I've made a teepee. There we go. Alright, delta V, 1.24 kilometers per second with a 20-second burn time. Okay. Okay, now let's try and figure out a little bit of drag. So, I'm going to say, looking at this rocket, I'm going to give it a coefficient of drag of, I'm going to be quite conservative here. We'll give it a 0.6. So we're going to try and go to slightly upper bounds. So 0.6 multiplied by 0.5 v squared. What kind of speed are we going to be reaching with this? Well, as it says, 1.24 kilometers per second. Take away that gravity. Although, again, with the burn time now dropping to 20 seconds, that gravity is going to change. So 9.76 multiplied by 20, we are only going to have a drop of 195. Let's say, for argument's sake, let's say it's 240 meters per second. So we'll drop to 1 kilometer a second. I don't think we're going to reach that. I think our average speed is going to be about 400 meters per second. So let's go 0.6 times 0.5 times 400 squared times rho, which was the atmospheric density. Now I'm going to go for an average atmospheric density. So let me think. If the atmospheric is 0.865, I'm going to say, let's say 0.8. And the area, the cross-sectional area that we're going to hit. Now, let's say we're going straight up. We are not going to be going exactly straight up, but let's just say that we are going to go straight up. So we need the cross-sectional area of that. Now, our width is 0.4, so the cross-sectional area of this is going to be pi r squared. So we'll just go pi multiplied by 0.2 squared. There we go. And this is telling me that the drag that we are going to experience is going to be around 5 kilonewtons of drag. Now that is a lot of drag if we look at the thrust that we actually have available to us. So, how am I going to work this out? Well, I'm going to do something that may not work, but I think for the purposes of this video may just give me the answer I need. So I'm actually going to adjust my specific impulse with an effective impulse, i.e. the drag. I'm going to take into account the drag that is bringing this aircraft down, or this spacecraft down. It's going to be an aircraft, this isn't going to go in space. So how am I going to do that? Well, the specific impulse, as I said, is going to be the total impulse over the mass, or the mass. I suppose we could do it as the could we do it as the mass flow rate? I guess it's the mass flow rate multiplied by gravity. So what we do is we do let me think. So we'll take the force, so the thrust that we have, which is going to be 11.9 take away, let's say 5. So we'll have 11.9 take away the 5, so we're going to be left with, what, 6.9? So that is going to be our thrust, 6.9, so we'll say 6,900. And then we're going to divide that by our mass flow rate. And our mass flow rate is going to be on this, which is 1.96 kilograms per second, but we need to multiply that by 4 because we have 4 engines. There we go. And then we need to multiply that by the gravity, so that is going to be 9.7. So our new, or 9.76. So our new specific impulse, our effective specific impulse, is going to be 90. Okay. So we now throw that into the rocket equation. So we'll say that we have 90 multiplied by 9.76 multiplied by the natural log of 141 over 55.8. That gives us 814 meters per second. Then we take away our burn time and the gravity. So we do 9.76 multiplied by our burn time of 20 seconds. Top speed 620 meters per second. There we go. Okay, 620 meters per second is what we are looking at, and I think that could be achieved. Now, is 620 meters per second going to be enough for us to achieve our 25 kilometers? Well, if I really want to work that out, I could probably throw it into a different equation. So I'll probably try right, so if I do 9.76 multiplied by the burn time, or minus the burn time, which is 20, multiplied by the specific impulse, which I said was now 90, multiplied by, oh, this is going to get really complicated, the natural log of, again, our 141 over 55.8, and then on the bottom is going to be, sorry, I am now literally trying to rearrange equations. Hang on, I'm just going to write something down. Bear with me. So T, I don't know whether that is correct. I'm going to guess this one, but I don't think I'm going to have gravity losses in this. 141 over 55.8, and then we're going to add onto that, that should be the gravity, should it? Add, so put that all in one of those, plus 20, which is our burn time again, multiplied by 90, and then let's see, take away 0.5 multiplied by 20 squared. That's bringing in Suvat equations again. And then no, I've done something wrong here. I think I've done something, yeah, something here is not quite right, unfortunately. Okay, that was annoying. I was attempting to do something, I didn't manage to do it, so I'm going to have to guess this. I think this could reach where I want it to reach, but I'm not 100% sure. What I'm going to do lastly is I'm going to add some fins. Now this is going to increase the drag, so this is going to make things a little worse, but there we go, it doesn't really matter. We're just going to have some small fins. Now the reason for these fins and the direction I've put them, I'm just going to have it push away from the village, because we need to push away from the village. That is all these fins are for, nothing else. In fact, I'm going to try and make them as narrow as possible to minimize the drag that we have on them. I think that should do the trick. Okay, lastly, let's go ahead and do some painting, because why not? Let's paint everything in a nice metal. There we go. This is going to be quite annoying if none of this works, and there is a high chance that none of this will work. Let's go ahead and do that. No, not straight. Oh, I could have done a straight one, and then that would work a little differently, but that's okay. Insulation, none. There we go. That can be smooth. And then this one can be hexagonal. In fact, no. If I make this, I doubt the texture is going to do anything, but if I go ahead and just rivet everything up, just looks a little bit better with everything just riveted. I guess this cannot have... Yes, it can. There we go. Job done. Okay, so with all the calculations done, I wonder if this will actually take off. Also, I'm just going to take a quick look at the pressures here, because if I just take that 69.9, I'll make that... No, I can just leave that at 69.9. I just want to do something, and 77.9. Maybe whilst we're flying, I will explain why the exhaust velocity that I was talking about, the equivalent exhaust velocity, was lower than this, and it has to do with these two pressures here. So I may explain that one. Anyway, let's take this off. I don't think we're going to reach where I want it to reach, but you never know. I think, personal opinion, with the drag, with the gravity, I think I've worked out the gravity correctly. I don't think it's going to reach that 600 and whatever meters per second I said. I think it's going to be about 500 meters per second. So let's give it a go. Let's also get a picture. Now I'm expecting this to rotate. If it doesn't, I'll be concerned. So I expect this to rotate. Come on. Oh, we're already out of throttle. Wait, never mind. My calculations were really quite good. But I do not think we can make the 25. Okay, I'm surprised. We are close to the 25. See, on the calculation that I made for determining the distance, I got a distance of 21, which is why I think I got it wrong. Oh, this is going to be terrible if I do not make the last... Never mind. Job done. And that is how you do rocket science. Okay, I'm actually quite pleased with the outcome of that. Very pleased with the outcome. I am going to, once we complete this, I'm going to try and do a... That is not good doing what I wanted to do. That is not doing what I wanted to do at all. Well, fine, just crash. I actually wanted that to fly away. I am surprised that... So, what did I say the top speed that... What was the top speed I calculated? When I took into account the drag? It was 600 and something, right? Let me have a look. I have a history of it. 620, and it reached more than that, which means the drag on the craft was less than I thought. Although that being said, obviously it may have been the right amount, the right coefficient of drag. It could have been the wrong average speed. It could have been the fact that the air density dropped off quite significantly, which it has. So there are a number of things, but obviously I just made some assumption to it. What are you doing? And why are you turning back towards the village? No, 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 no. Please do not turn back towards... It's turning back towards the village. If this thing flies all the way back to the village through these mountains and then hits the village, I'm going to be very disappointed. It is doing the flying thing that I wanted. It's just that it shouldn't be pivoting left, right, left and right the way it is. That is the problem I'm having. There we go. Okay, end flight. We're not going to be able to recover craft. We're going to save that flight. And that is that one done. We do have a flight termination system. Reach 30 kilometers. 30 kilometers above ground. So for that, if I give myself an extra... I might just do this, just this one. If I do that, I can probably bring this up actually to about 220. Still under the 6k. And it said reach 30 kilometers. So I'm actually going to make an adjustment on these wings. They're not doing what I want them to do quite in the way I want them to do it. There we go. That might behave a little bit better. Okay, let's go ahead and try that again. I'm so surprised that my calculations were pretty much... Given that I have not done this in a very, very long time, those calculations I'm surprised at. Right, so we should reach the whole... Oh, I didn't even accept the contract. Can I accept it from here? You cannot... Oh, rubbish. Retry, undo. Undo and exit. I didn't even accept the contract. How do I accept the contract? Career. Accept. There we go. Let's try that now. Once again. That was stupid. So my science wasn't quite bang on, but it wasn't too bad. Right, the idea here is we need 30 kilometers. Oh, it's AGL, not ASL. Okay, well, the best thing to do here then is to be able to get to, I don't know, above a little valley or something. Anywhere where there's a valley? Because if we can do that, then there we go. 20. Yes, that's it. That is what I want. Come on, come on, come on. There you go. Okay. So select the command disk. So that's one there. Press that. Explode. Click again. Kaboom. Job done. Piece of cake. Piece of cake. Save flight. And should we do one more if there is one? Going sideways. Launch new craft. Start grounded. Crash at least 30 kilometers away. Okay, slight adjustment to this this design. First off, let's get rid of these rivets. Let's bring a little bit more to this. Not cross beams, not insulation, not grooves. Yes, let's have that as a simple. Let's have this one as none, maybe, or can I do none? None. There we go. and then the bits in the middle with rivets, and see how that pans out. Right. So for us to be able to get 30 kilometers away, I no longer need much upwards acceleration. So this is what I was explaining earlier about sideways acceleration and taking into account the sign of your thrust and giving you thrust vectors in X, Y, and Z direction. So what I want to do here is I'm going to use these to try and push the nose over and give us more thrust in the X direction, pushing us away from the village as far away as we can go. Now, already we reached, was it 25, nearly 30 kilometers away, but I need to push slightly further just in case this turns back on itself. And that is what I need to be aware of. So let's go ahead and do that again. See, once you've done the calculations, nothing to worry about. You just go for it. So let's go ahead and launch. Oops. There we go. It's slightly weird setup there. Right, I need to be watching where this is going. And this is doing exactly what I wanted to do. As you can see, that tilt is now somewhat stronger. Please rotate around. Please rotate around. If you don't, I'm going to be in trouble. I am in trouble. That hasn't rotated the way I wanted to rotate. It has now. And if it can stay like this, it should push the nose down and we should begin flying. It's wobbling. It's wobbling in a way that I'm not happy with. It's doing it again. Right. I'm not happy with that wobble again. But it's okay. We should, as you can see, we are very, very far away. As long as it doesn't turn back, we should get a fair distance away. Currently 22 kilometers away. 23, 24, it's slowing itself down. Okay, the wobble's slowing itself down. That is good. Is it going to regain enough control? Is it going to lift? Is the nose going to lift? I need the nose to lift. Never mind, we've still made the 30. There we go. We've made the 30. Exactly as we wanted. There you go. You could not get any closer than that, or any more perfect than that. We'll recover that, and that is where I'm going to end this video. Thank you very much for watching. What do we have next, actually? Wet rockets. What? Polluting the oceans is bad, but getting complaints from the neighbours about things dropping in their lands is worse. Oh. We may need to look at some of the tech points or the tech tree. So, in the next video, I'm going to look at the tech tree. Thank you very much for watching. Please remember to hit the like button if you like this video. Subscribe to the channel for more videos on Juno New Origins. Leave a comment in the comments box below letting me know what you think. Don't forget to support me on Patreon if you can do so at www.patreon.com/ECGadget. Your support would be massively appreciated. It would really, really help me out. And also, you can find me on social media at ECGadget LP for both Twitter and Instagram. That is all from me. Oh, actually, lastly, you can join my Discord server. Link to that is also in the description box below. That is all from me. I am currently staring at one of the equations. Okay. So I'm staring at one of the equations and trying to work out why my distance calculation was off. And I think it's to do with the fact that drag is not included in this distance calculation. So I need to somehow adjust that to add drag. So that could be a little awkward. Oh well. Anyway, I will get back to scribbling notes on a piece of paper. And I will see you next time in Juno New Origins.